As you can see from the slide, our speaker today is steeped in physics. The dictionary definition of imperfection carries negative connotations, such as defect, fault, deformity, blemish. Today, one of the University of Colorado's Nobel Prize winners in physics, Dr. Eric Cornell, is going to tell us how an imperfection that occurred some 14 billion years ago made it possible for us to be here today. And what a team of young Boulder scientists is learning about that imperfection, which is actually quite beautiful. Dr. Cornell, please come up.
Thank you so much for having me come to your Rotary Club. I'm very flattered to be here, very excited. I'd like to tell you about some of the things that we're working on at the University of Colorado, partly at the University of Colorado, partly at the National Institute of Standards and Technology. My position is sort of half and half. I want to start with how things were 14 billion years ago, 14 billion years before a particular Rotary Club lunch talk. Life started with a bang. Shortly thereafter, things started to form in the universe. Many of us will remember that, I'm going to oversimplify a little bit here, but everything is made up of electrons and protons and neutrons. Stick them together and you get atoms, stick atoms together, you get molecules, put the molecules together, you get everything else in the universe, right? Back in those days, at the very early days of the universe, yeah, the void of space was jam-packed full of electrons and neutrons and protons, but also their partners. For every electron, there was an anti-electron. There's this stuff called antimatter. For every proton, there was an antiproton. For every neutron, there was an antineutron. And there was vast amounts of this stuff. We don't see very much of this so-called antimatter these days, but back then it was copious. There was just about the same amount of antimatter as matter, and the universe was filled with billions of times more stuff than it was today. The universe was really quite full. What happened then is the universe started to expand. And you may remember from high school chemistry, and that actually was the last time I took chemistry was high school, is that when things expand, they cool off. And after they cooled off, let's see if we can see the, who's clicking the slides over there? Oh, there it goes. The universe expands and cools, and you can tell it's getting cooler because it was red and now it's kind of blue, and it's a little bigger. And then one more time. And then something very romantic happened. Yeah, isn't that sweet? The proton found, and every proton found an antiproton. Every neutron found an antineutron. Every electron found an anti-electron. It's true soul mate. But married life is passionate but kind of short. These were problematic relations. Well, what happened is these particles, as they stuck together, they would pop, annihilate each other. When a piece of matter meets its opposite piece of antimatter, it sticks for a second and then it explodes into a hail of light. Nothing, the matter disappears altogether, there's nothing left by light. And one after another, that's what happened to all of these short-term relationships. And basically, what was a universe full of matter basically all disappeared. So one more. In this mass cosmic wedding that happened shortly after the Big Bang, we're talking just a few minutes after the Big Bang happened billions of years ago, there was somebody for everybody. Or, wait a minute. Oh, what's going on here? Oh no. This is kind of sad. There was here and there an electron, a proton, a neutron left over that didn't find its true soulmate. Almost everybody. So who are these few lonely particles that nobody wanted? Yeah, they're you. Right? That's why we're here in the universe, basically, is because the universe was almost perfect. There was exactly the same amount of matter, antimatter. There was an electron for every anti-electron, a neutron for every neutron, and so on, except there was this tiny imperfection, this slight imbalance. This imperfection had enormous consequences. It's why we're all here. It's why there's a universe of planets and stars and all the stuff we see in the universe, including us, because of this tiny early imperfection. So what was nearly perfect was not exactly perfect. Okay. We were born, you could say, of this original imperfection. It's a little Psalm 51 for those people who are into that kind of thing. So what do we make of this? How can we understand this? It's not easy because it happened 14 billion years ago. You want to study this thing in nature, which was responsible for all for us to be here, but there aren't any time machines for us to go back to have a look. So there's a couple different ways. One is you can use telescopes. Telescopes are sort of like a look back in time thing. When we look in a telescope out into the sky and we see a galaxy which is 10 million light years ago, it's like we're seeing that galaxy not as it is now, but 10 million light years ago. And now on the cosmic scale of things, 10 million years is not so long, but if we look back to see the very, very farthest thing, we get the world's most powerful telescopes and stare deep into space, the farthest galaxy we can see is 13.3 billion light years away. It means we're seeing that galaxy as it was when the universe was just a tiny fraction of how old it is today. So we can kind of look back and take a picture of the early universe, but not nearly early enough. With this thing, when this imperfection, this all-important imperfection happened, that was earlier yet. So another approach we could take was we could use particle colliders. These are called accelerators. Physicists take protons and antiprotons and accelerate them and smash them into each other. And right when they smash together, that violent moment is kind of like the early universe. So here is a picture of the largest scientific instrument ever built. It's called the LHC, the Large Hadron Collider. It's partly in Switzerland and partly in France. It costs something like $10 billion. And it was apparently not good enough to answer this question. I'll let you in on a little secret. There are no particle physicists in the audience because this is a little bit, I'm not sure if it's consistent with the 4 Rotarian principles because, in fact, it was a little bit disappointing, this large thing. The people were sad about this. It was a bit of a letdown. It's exciting. I mean, people, you might have heard about seeing the Higgs boson, but everyone was kind of expecting a Higgs boson. They were also expecting a whole zoo of new particles, which would help us address some of these early questions, but that didn't turn up. So is there a third way we can go back and look at the early universe? And I'm going to call it like looking for fossils. When we want to look for dinosaurs, we can't, there are no written records of dinosaurs. There's no papyruses or something where people wrote down. You can't go back in a time machine, but you can find the bones of the dinosaurs and you can draw all sorts of conclusions about what dinosaurs were like. What I'm going to talk about is looking in the laboratory today for the fossils, the bones of this early imperfection. So what we're looking for is a remnant of this ancient asymmetry. And symmetry is all over nature. This is a beautifully symmetric snowflake, but I'm actually talking about more elementary symmetries. Just a second. One of the big symmetries in nature is that electrons seem to be just like electrons, anti-electrons, and that when you look at particles in the mirror, they look just the same. Now, most people, when they look at themselves in the mirror, they can't tell whether they're looking at themselves or a photo of themselves or a reflection of themselves. I have no difficulty in this respect. When I look in the mirror, I see someone who looks entirely different from me, someone who is missing a right arm. This happened about 15 years ago. I can't say whether or not it's a coincidence that right around then I started studying this ancient imperfection. I got all interested in asymmetry all of a sudden. Okay, so this is where I'm going to sweep a lot of stuff under the rug because this is not a physics lecture but a Rotary lunch lecture. There's a key assumption. There's a group of physicists who are called theoretical physicists. They try to create mathematical models that explain everything all at once. They try to explain the early universe and they try to explain particles these days. And it turns out to be very, very difficult to explain an ancient early asymmetry, like what caused our universe to exist, without also explaining or predicting, if you will, that modern day particles, the electrons, the protons, the neutrons around us, aren't also asymmetric. It's really hard to put those two things together. So there's this whole class of physicists. I'm a physicist, but I'm an experimental physicist. As an experimental physicist, I work with screwdrivers and soldering irons and lasers. The theoretical physicists work with oscilloscopes and pencil and paper and computers. This whole class of theoretical physicists say, you know, Eric, we really think that if you would look very, very carefully at modern day particles, they ought to be asymmetric. And if you could see that, it would help us understand this early imperfection. I said, okay, we can do that. So we picked the simplest particle we know about, the electron, which is, it's electrically charged, negative. Many of you know that. It's got some mass. It turns out to be spinning, which means that when you take some electric current and you move it around in a circle, you get a magnetic field. It's got a north pole and a south pole, just like the Earth. And the question is, the symmetry question is, are the north pole and the south pole just exactly the same? The Earth has a north pole and a south pole, and they're really different. The south pole has got mountains. The north pole has got sea ice, or it used to, less so these days. The north pole has got polar bears. The south pole's got penguins. If you ever see polar bears and penguins in the same place, you're either at a zoo or you're seeing Photoshop. Celeste and I were actually just down in the southern hemisphere and we saw penguins, so penguins are much on my mind. They're really cuter than they look in person. Anyway, is the electron maybe also asymmetric? So we'll go back to the electron. Maybe, just maybe, if we were to look very, very carefully at the electron, we'd see that that sort of electrical charge is actually a little closer to the North Pole than the South Pole. Another way of saying is that the electron might not be completely round, but more sort of egg-shaped, fatter on one end than the other. So if people have looked to do that, and when they look, they say that, well, if there is that difference, that tiny asymmetry, it's really small. Even 14 years ago, people knew it was very small. Sort of along the lines of, if it's there at all, it's kind of like, imagine you had a perfectly spherical, like the cue ball on a pool table, perfectly spherical Earth, except that on the North Pole there was a little extra stuff about the thickness of a human hair or something like that. That would be still a pretty round Earth if it was just a little thicker on the South Pole by the thickness of a human hair. That's the kind of weird, tiny little out of roundness we're looking for. So we're looking for that, and we do that using molecular ions. We're molecular spectroscopists. We take these electrons, we embed them inside molecules, and shine laser beams at them, and we look for tiny asymmetries. And when I say we, what I'm really talking, first I'll show you the apparatus. There's a room full of stuff about the size of this stage here behind me, and it's mostly full of lasers. And in the very back corner there, you can see there's lasers, and in the very back corner there's a little vacuum chamber which is full of these molecules that we're studying. Okay. The apparatus is, I'm just going to say it's pretty complicated. And I'm just going to guess, and you can tell me if I'm way out of line, that you're not going to want me to walk you through every aspect of this. Suffice it to say that I've been working on it for 15 years, and it's pretty darn complicated. It involves a huge team of people, and I'm hoping that team will show up here in a second. Here's one more picture of the apparatus, I think. Yeah. You know, fortunately, we have also computers on our team that turn the lasers on and off, turn the various microwave fields on and off, trap the ions, and eventually dump them out. Yeah. I so much want to show you this group that I'm even going to come over here and see if we can we just pop open can we go back to the slide sorter mode? I think, can you pop out of the screen and go up one or two? Just kind of scroll up a little bit. Keep going. Oh, where are they? Let's scroll down again. Let's scroll all the way down. Keep going, up a little bit, down a little bit. There, click on that one if you will. Yeah. Sorry about this. Okay, I think a thing to emphasize is that this experiment is very, very complicated. To make it work, we need a large team of really talented people. These people are mostly, but not all of them, graduate students in their 20s. And they've come to the University of Colorado. Yeah, they're here to measure the asymmetry of the electron, but what they're really here to do is to get like extremely high-end technical training. So at the end of like putting in 4 or 5 years trying to see whether or not the electron is asymmetric, they come out being, I hope I can say this in Rotary Club, all around technological badasses. They know how to do stuff. They can get things done. And if you think about it, like if you want to sharpen a knife, you don't take the knife and rub it against a stick of butter, right? You rub it against a whetstone. You need something really to give you some resistance if you want to hone the edge of an intellect, to hone the edge of a technological talent. So basically, these people come to Boulder to work on one of the hardest problems there is. This is a fantastically tricky thing. By the time they're done working on this, they think, and I kind of agree with them, they can do most anything. So a lot of these, this is people who are in the lab now and have been in the lab recently. They are just looking around there. I see they come from, I want to say 5 different countries. They've gone on to become a professor at Harvard, a professor in Singapore. Several of them are working on the tricky problem of quantum computing in local high-tech companies here in Boulder. Others have gone on to become teachers. One has started a company. So this is sort of in some sense the real product of my lab. Can we somehow get back into where we were? Sorry for this jump, discontinuity here. Let's see if we can come out here. So can we go up one slide from here? Yeah. So we put this all together. We made this measurement. And somewhat to our disappointment, hang on one second. Arm is flapping around, getting on my nerves. Somewhat to my disappointment, when we measured it, we found that, well, if this electron is out of round, we made a measurement, it's still consistent with being perfectly round, but it's now a much more accurate measurement, about a factor of 15 more accurate. This was the day when we finally admitted to ourselves, we're happy because we've wrapped up the experiment, we admitted to ourselves that we measured 0. It's still 0, but with much, much smaller error bars. All right, next slide, please. This experiment and various versions of this have attracted the interest of scientists for many years, actually going back almost 60 years. And on here, you can see the numbers 10 to the minus 24, tiny, tiny number. 10 to the minus 25, that's a 0 point with 25 zeros after it. These are not actually the measured values of the electron as we go through 1965, 75, 2005, up to the present day. These aren't the measured values, these are the limits. This is like how close to 0 we think we're getting. For about 20 years, you can see the various measurements didn't change at all until a series of measurements came along. Next slide, please. One was done by Harvard and Yale. Next slide, please. And one was done here at University of Colorado at Gila with NIST. You can see those 2 dots are about the same, and they happen a couple years of each other. It has been something of a competition in the physics world to make this measurement better and better. People here in Boulder, I expect a number of you are graduates of the University of Colorado. It will not surprise you to understand that in order to compete with the University of Colorado, Harvard and Yale had to team up. Go Buffs. So we made this measurement. This was as of about 2 or 3 years ago. Next slide, please. The consequence of this is Harvard and Yale on the one hand, and Gila at the University of Colorado, we were accessories to the murder of the minimal supersymmetric model. What do I mean by that? The people who think about particle physics came up with a model called supersymmetry. It was a very, very fashionable model. Everybody liked this idea. It was sort of the Paris Hilton of physics. It was glamorous. It was on every newspaper, it was on every magazine cover in physics. and yet there was no evidence for it. And when we finally went to look for it, in sort of two places, both in these kind of measurements that I'm discussing, these sort of fossil measurements, these very precise measurements, and also in the smash them together at the collider measurement at the LHC. No evidence for it was found. So basically this model is now, if not exactly dead, at least it's now very unfashionable, like Paris Hilton. Anyway, kind of out of the picture now. So that happened. Next slide, please. And then another slide. And then, meanwhile, there continued to be more pressure. And meanwhile, this group at Harvard and Yale did, this doesn't look like very much of a change there, but that's another factor of 10. They did 10 times better than us. I don't know how many of you still watch television, but next slide, please. That's just rude. Okay, next slide, please. We decided that we need to, this sort of friendly competition, I'm making sort of a joke out of it. These are actually my best pals. When we go to conferences, we all hang out together and tell Electron out of roundness jokes. We decided we have to catch up with them because the sort of the pressure from this other half of the world of physics is relentless. We still, it's almost like whining, we still think the electron should be out of round. Couldn't you please measure it just a little better this time for sure? And you know, like Lucy in the football, we fall for it. So we have, next slide please. This one is not filled in. We have plans for sometime in the next year to do about another factor of 10, please. And then next slide. Somewhere into the middle of this next decade, right around the time I'm going to retire, this is going to be the my final statement on that. If finally in there we could see a number which was non-zero, it would be back to Stockholm for me, baby. and of course, even if we don't, is the point, we're limiting, we're ruling out, we're providing constraints for this whole other half of physics, which is trying to understand this ancient picture, this ancient mystery. Next slide, please. So we are left with this mystery still. It's one of the great mysteries of cosmology, of cosmogenesis, as they say, the beginning of the universe. While we're working on it, people sometimes say, Eric, you've been working on this for 15 years. You keep measuring zero better and better. Is that not frustrating? Next slide, please. And one more. And one more, and one more. And I say, no, it's not, because properly understood, what we're about is inspiring folks like this to come in and tackle something which seems impossible and yet still make, you know, significant progress, factors of 10. You know, imagine if you were a factor of 10 more wealthy, or if your car went a factor of 10 faster. Factors of 10 are huge factors, right? These require brilliant ideas, an immense amount of work, and basically people sort of at the very, very cutting edge. And these people here are starting as very talented people and finishing their studies here in Boulder as basically world technological leaders, which is really what I see my job as doing, is training those people. So at this point, I am going to pause and ask for any questions you might have. And I want to say that, like, all questions are on the table. If you want to ask me what happened to my arm, that doesn't bug me at all either. So, yeah.
So, fellow Nobel laureate Steve Weinberg,
Yes.
in his book, The First 3 Minutes, says that the more he studies physics or the universe, the less meaning he finds, less purpose he finds.
Uh-huh.
I wonder if you share that sentiment.
I will say that I actually don't look, like, meaning is important to me, but I actually don't look for meaning in my studies. I look for it in my life, I look for it in my family, I look for it in other places. I never went into physics, I went into physics looking to find a robust intellectual challenge. For meaning, I look elsewhere.
Well, all of this work depends on the assumption that at the Big Bang there was a whole lot of antimatter created. What evidence is there for that?
Basically, it's if you, again, no one was there. You can run the clock backwards. I mean, there's a couple things you can do. One is you can look out into space, and if you look deeply out into space, what you notice is that photons are coming from us every which way. There's this thing called the cosmic black body radiation. There are many, many more photons in this universe than stuff. And these photons are coming from all directions, and those photons are, you can look at them, you can see patterns in them. They're all fully consistent with the idea that there was, at the time when those photons were first created, the universe was massively more dense. There were at a time when there were no stars or galaxies. Everything was sort of too hot for things to clump together gravitationally. And you sort of keep running the clock backward from there, just imagining like what could have led to that. Basically, it's sort of a series of steps of inferences. I think sort of the furthest back we can, quote, see is looking at this sea of black body photons called the cosmic microwave radiation, which is not structureless, which has all kinds of patterns written onto it. And those patterns are completely consistent with the model of a universe expanding from something very close to a point. And if it has been doing that, then at those very, very high temperatures, things were crashing together so fast that there surely must have been, we know what happens when particles crash together. You have matter and antimatter in huge quantities and almost the same amount.
So,
Oh, sorry.
go ahead.
Sorry, I didn't see.
How do you select your team?
My team, how do I select my team? Various different ways. For the graduate students, they apply to the University of Colorado Physics Department Graduate School, and I go and read their applications, and then I interview them. And I'm looking for people who are lively, who bring a new perspective, who, I like them to have a good academic record, but that's not necessarily the most important to me. I also look for people who I think can work well with other people. These experiments are infinitely too hard for me to do by myself or any 2 or 3 graduate students to do. They have to be able to work together in a group of 5 or 6 at a time cooperatively. So I'm looking for a lot of different properties. And then for the postdocs, who are kind of like the equivalent of medical residents, they are usually done their graduate school projects somewhere else in another university. Oftentimes I go to conferences and I see them present their graduate work at conferences, and I'm always scouting. When I go to conferences, half of why I'm there is sort of as a recruiting trip.
Great. Hi, Eric. 3 questions.
Yes.
You've got a complex mind, so I'll just name one. The first is the universe still expanding, or is it beginning to contract? That's one. The second one, go ahead and talk about your arm, if you will, because a lot of times when you talk about imperfections, you talk about changes. We all know people who have like something dramatic.
Mm-hmm.
You had 2 arms, now you had 1.
Yes.
But it did not stop you. In fact, it actually helped you drill down maybe even more. So if you talk about that human side of what happens, some people might just be completely derailed from life. You were not. You went on to a Nobel Prize, because of your work. And then the third thing is, I noticed the team because I deal in leadership and I deal with the synergy between people who have a broad range of traits from one side to the other of the spectrum, I would say. You had this incredible mix of, there was a time in education when STEM was putting millions of dollars in to get women into science, technology, math, and so forth. You have a good balance. Does that balance add or contribute anything to the complexity and the ability to manage and understand and drive you toward the solutions you've found?
Sure. So in order, yes, we absolutely think that the universe is still expanding. And it used to be people thought maybe the universe would expand, come to a stop, and then coming back to what they would call the big crunch, going the other way. No, they don't think that anymore. They think that it's going to keep expanding forever. But that's not something to worry about unless you have a sort of a 30 billion year investment time frame. That's a long time even for a house mortgage. I'm going to jump out of order a little bit. I find it super important to have a wide range of people and backgrounds working in my group. People are good at different things, and if you go for too much of a a monoculture in your crop. You know, you're vulnerable to like the tobacco virus or whatever it is that comes through. And so you want people, you have a more resilient group if it's a group that brings different skills and different strengths. It takes a little while to blend those people together, help them bring the best out of all of them, and it's more or less my main job, more than thinking about the beginnings of the universe. So that's, I find very, and then I'm also just sort of committed from the point of view of fairness and the kind of society I'd like to live in, to have to see a lot of different kinds of people pursuing physics. Second question, going back to, is the arm? Yeah, just to be clear, I lost the arm after the Nobel Prize. So it wasn't that the arm spurred me on to the Nobel Prize. That was, I lost my arm in the year 2001. It was a terrible blow. You know, I was, sorry? So lost my arm in 2004. Thank you. Nobel Prize was 2001. Yeah, lost my arm in 2004. Celeste was there. She probably got it right. And I won't lie, it was quite a shock. The smart money was betting that I would not survive. You can't see that. It's not just the arm. If you look across, the vast majority of my torso is covered with skin grafts. The physician who was treating me at Boulder Community later said that I was the sickest patient he ever treated who went on to survive. So it was very, very close at the time. And so, and it required, I was in a coma for several weeks. And in fact, it was while I was in a coma that most of the surgery happened, including the amputation. So I woke up and it was, I was sad, right? First of all, by the time I woke up from the coma, I was on the rebound, and my family was coming to see me, and they were all happy because I was getting better. I was, only then coming to grips with how sick I had been, and my arm was missing. I was feeling sad about it, but it didn't take very long for me to think that, all in all, I was more excited about being alive than I was sad about losing the arm. It took coming back was a lot of work, and I benefited from having an enormous amount of support from my family, from the broader community. I felt just a huge outpouring of love, of people caring about us and so on. And Celeste here in the audience was an enormous impact on that, had an enormous impact on that, but it was a certain sort of love, also a particularly productive one. I'll tell you a story. I've been in the hospital. I was in the hospital for, gosh, I want to say 7 weeks, and I was back only 3 or 4 days, and was still wrapped up in bandages, bleeding through my bandages most nights, and so on. It was still a very difficult time, but we were trying to bring sort of normalcy back to our lives. And I was having dinner at the dining room table, and we were having hamburgers, and I wanted to put ketchup on my hamburger. So I took the ketchup bottle, which had the cap on it. Well, how am I going to take the cap off? And I passed it to Celeste. And I said, Celeste, would you take the top off the ketchup bottle? And I'm going to use this as a pretend ketchup bottle. She took it, and with one hand, and looking me in the eyes, she held the bottle, and with her fingers, she took the top off, and she handed me the ketchup bottle, having taken the top off with one hand. I was called out. That was tough love. It was clear that feeling sorry for myself was not going to work very well in this household. So it was that sort of thing. So there were many, many, many good things that happened. The loss of the arm is an inconvenience. The skin grafts can be an inconvenience. There's some neurological things associated with it. On the whole, it's not even close. I'm thrilled to be back. I've learned how to do essentially everything with one hand, for instance. These are not stretchy shoelaces. These are not Velcro. These are honest-to-God shoelaces, people, and I tied them. On the other hand, you will note that my fingernails are very nicely trimmed, and I did not clip them. So there are a few things that I've yet to figure out how to do, but almost everything I can do.
How is your research funded? That's most relevant.
How is my research funded? Because of the sort of, this is a problem in precision measurement, some of the funding comes in-house from the National Institute of Standards and Technology, whose business is better measurement for industry. And so they are, a small fraction of their funds go to, call them sort of cutting edge, a little out there projects. And let's face it, my project's a little out there, but which challenges the capability of metrology. They find that worth funding. So some comes from that, some comes from the National Science Foundation. This is very much a fundamental science question. There's a private foundation funded by Tom Marsico of the Marsico funds that funds some of it. And over the years, various other funding agencies have contributed. I'm looking, actually exploring some other foundation funding options just now. It's tricky, you can imagine having a group of that size. They are, I'm paying all of them, right? So they are going to school, and at the same time they're getting their tuition covered and a stipend. It's a significant budget, and almost all, I'd say 80%, although we have a lot of lasers, and the lasers aren't cheap, almost all of my expenses in running this are for salary. One thing I forgot to mention, because I had the wrong slide up there, is that I keep saying which is very unworthy. First of all, there's the team, which I showed you, but the other thing is that this is a 2-professor experiment. I've been working on this for 15 years with my colleague and very good friend, a guy named Jun Yi, who's perhaps the world's best laser spectroscopist, works here in Boulder, and he and I have been co-equal partners on this now for I don't know how long. He also takes half of the responsibility for shaking the money tree to keep these things going. The real answer to who is paying for it is you, right? If you're paying your taxes, I thank you very much, because almost all of it's public money. Yes.
Could you tell us what you were working on at the time that you got the Nobel? I bet the audience would like to know.
Okay. When the dean tells me to do something, I pretty much have to do it. At the time I got to Nobel, I was not working on this project at all. I was working on the world's coldest stuff, which could be even more than a whole nother Rotary lecture, and I don't want to do that, but it was called Bose-Einstein Condensation. Basically we used a combination of lasers, again, and magnetic fields to make a gas. In our case, it was a gas of the metallic vapor of rubidium. We cooled it to temperatures which no one had ever seen before, and at these very lowest temperatures, and we're talking billionths of a degree above absolute zero. You may know that there's the lowest possible temperature, and we got to within about 20 nanokelvin, which means 20 billionths of a degree from absolute zero, 273 degrees Celsius below freezing. So at that very, very low temperatures, the atoms stop acting like little pool balls bouncing off each other, and they act more and more like waves. And this thing which we saw, called Bose-Einstein condensation, was sort of the ultimate triumph of this waviness. All the atoms in our sample lined up in one giant wave. I think of them as sort of acting like the individual hairs in a huge Reagan-esque pompadour, all sort of piled up, all lined up together. And yeah, so that was called the Bose-Einstein condensation, which first happened in 1995, getting to be a few years ago. I've been in Boulder for a bit, and was recognized with the Nobel Prize, along with my colleague Carl Wyman, who's since left University of Colorado, alas, but is still very active, and Wolfgang Ketterle at MIT. The three of us sort of all worked on this project. We have our own special Rotary Club, actually. I think it's 5, if I'm not mistaken, but 2 of them are, I would say, sort of semi-retired. So they're one, and a couple have, well, 5 have been awarded here, but 2 have moved away. My friend Dave Wineland moved to Oregon, I think largely for his wife's health, really. She should be at lower altitude. And Carl Wyman, my longtime colleague, went to work for the Obama administration. And then when that was done, took a job at another university, which we won't even name. And then, John Hall is still around here in Boulder, somewhat retired. Tom Check, also still active. So we don't actually get together and have dinner parties or anything like that. Every once in a while, the university or NIST will say, let's have like a photo opportunity or something, and that will happen, but it's not so very common.
Eric, I want to thank you so much for responding to our call and from the program committee and bestowing this fascinating lecture or talk on us today. And the Q&A period was equally as fascinating. So thank you so much for honoring us with your presence here. So it's been 26 years now since Rotary had begun the work of trying to eliminate polio from the face of the earth, and we're very close now. And in honor of your participation here today, we'd like to contribute 100 doses of polio vaccine to the Polio Plus Fund.
Wonderful.
Thank you.